right. Welcome, everyone. It's our honor today to have Professor Frank Giraldo present at the finite element LLNL seminar. He's a distinguished professor at the Naval Postgraduate School in Monterey. He also runs the Applied Math department, correct? Worked for a long time in high-order spectral elements, famous for climate modeling, the NUMA code. One fun fact about Frank, I was at NPS recently, and I went to the library to have a call. And in the library, you can see Frank with his new book, full-scale picture. That's another level. So, yeah, you just got a couple of years ago a book on methods for tensor product elements. So today he's visiting us for the full day. If you want to meet with him, we still have some slots available. Also, let me know if you want to join for lunch or dinner. But today he's going to talk about DG methods for hurricane modeling, I will say. And yeah, it's a real honor to have you here, Frank. Thanks for coming. So please take it away.
Thank you, Zanio, for that very nice introduction and for the invitation to come speak here. It's my first time at Lawrence Livermore. I think, well, I was here last year, but I think I just made it to one of those outside gates and we had all our meetings over there. Okay, so let me just tell you about what I want to talk about today. I've been working on these element-based Galerkin methods for many years, and we've been trying to apply them to geophysical fluid dynamics models, particularly weather prediction, and now we're looking at things like hurricane intensification. So let me explain to you what I mean by that. However, first you have to acknowledge your funding agencies, the work on the hurricanes, the work on the hurricane work that I'll be talking about today, and this multi-scale modeling framework is funded by ONR. The work on kinetic energy preserving and entropy stable DG methods is work funded by NSF. And here's a list of our collaborators in both projects. I don't know if you can see my mouse, but so the most of the work, my talk today would be based on this NUMA model that we've developed in my group in the math department at MPS, which is basically the dynamics used in the U.S. Navy's Neptune model that will go in operations by the end of 2024. More information can be found on this website here, or this QR code here. I also will talk about this lighter weight version of NUMA called XNUMA, which is the work that, or the model that we've been using primarily for this multi-scale modeling framework. Okay. There we go. Motivation. Now, let me tell you why we're doing this work. So hurricane rapid intensification is when the maximum wind velocities exceed about 30 miles per hour within the first 24-hour period. And this continues to be a very important topic in weather and climate for a variety of reasons, right? Dealing with extreme events is a big deal. And the reason why hurricane rapid intensification is such a hard problem is because to capture it properly requires large eddy simulation models that on the order of 100-meter resolution. And we're talking about domains that are hundreds of kilometers in size, and the delta x has to be about 100 meters. And you want to make sure that those models run stably and with as little dissipation as possible. Just to show you what I mean by that, I have two plots here on the left and on the right. On the left panel is on the horizontal axis the time in hours for a 6-hour simulation, and on the vertical axis is the wind velocity, the max wind velocities. And the WRF model that I'm showing you here is actually the model being used by the National Hurricane Center. And one of the things that we have recognized, we've written papers, there's a paper down here, a reference down here, where we actually compare NUMA to this WRF model. And we know that WRF does not do a very good job of capturing this rapid intensification. And when we use other models, for example, let's say the NUMA model, which is a higher order model, we get a much larger vertical max velocities. Now, it doesn't mean that I'm telling you that the green curve is on the money. It's dead on accurate, but it's certainly giving us the kinds of velocities that we would expect in rapid intensification. And the paper that's referenced down here we actually go through and show why that happens. And it has to do very simply with the way pressure gradients are handled in low order models. If you can't do that properly, you're not going to be able to get the same dynamics that you ought to get. And on the right, I just show you basically an XY slice of a 3D simulation of a hurricane that we've done with NUMA. Okay, so we know that we need large eddy simulation. We need to run stably and with as little dissipation as possible. Now, running a CRM is a cloud resolving model. That's about kilometer resolution. Is still too expensive to run on a regular basis. So the simulations that we did in this reference down here, we ran at order 2 kilometer resolution. It had about 80 million degrees of freedom, and you have to run it for a very long time, right? So the LES version of that would require about 32 billion degrees of freedom with a time step about 20 times smaller. So we're talking about 10,000 times larger problems. So here's the expense we're talking about. So to run such simulations require different strategies, right? If you want to run it on a regular basis to be able to do actual science, you have to resolve fine scale. You want to resolve fine scale features. How do you do that? You want to do, you want to think about time integration as a way of giving you a faster time to solution. And of course, high performance computing is an absolute must, as we all know. Let's see, okay. And just to show you the equations that we are talking about in this talk here, it's essentially compressible Euler, right? And maybe not the form that you're accustomed to seeing it. Now, the reason why I show it to you in this non-conservation form is because that's the equations that's being used by the US Navy's Neptune model. And so we're trying to stick to the same equation sets that they're using, because we're hoping that whatever we do here will actually be leveraged by the Navy models. And the slightly different thing that you probably haven't seen before is that the thermodynamic variable, instead of being total energy or internal energy, it's basically something called potential temperature, which is just some form of temperature. And then finally, we have a bunch of equations for moist variables. So for example, in the simulations I'll show you today, we have water vapor, we have condensation, which become clouds, and then we have precipitation, which is rain. And NUMA, because it is a research code, we carry a lot of different things, right? It's not just this equation set. We carry an internal energy form of the equations. We carry a couple of, and that's only used for space weather applications. We just finished a project with DARPA on using these equations for space weather. And we have 2 conservation forms, and those forms are used really only for the entropy stable work that I'll show something about towards the end of my talk. Okay, I'll now to the topic that is near and dear to my heart. And since I'm in the MFEM seminar, I think we're all, I'm preaching to the choir here. But so the work that we do is to approximate the spatial derivatives of your PDEs. We use element-based Galerkin methods. And the idea, very simply, is you have a global domain, omega, and we subdivide that domain into a bunch of smaller elements, omega sub e. And inside each of these elements, we construct some basis functions. Well, we lay down some grid points so we can actually construct basis functions on. We use Lobato points in our work. And we then construct cardinal functions on each of those Lobato points that look something like these down here. And these are Lagrange polynomials, right? Nodal approximations. And then once you construct those basis functions, then you can approximate your solution vector Q. The subscript n is for nth degree approximation of Q, and the superscript e is for an element that's defined for all x and all t. And we define this finite dimensional expansion in the following way. Okay, that's standard stuff. So now let's think about writing our governing equations in some general divergence form. So this is more a Balance law, right? It would be just a conservation law of S is 0. So for general, you have a Balance law. And then we approximate the solution Q by the basis function expansion I just told you about. And if you have things, for example, like fluxes and source functions, then we just plug in our approximation of Q into these functions, functionals of Q. And then once we have those, we plug them back into our original continuous PDE, and we end up with a residual that looks something like this, right? And the residual is non-zero because this is a finite dimensional expansion. So the trick then is to multiply R by a test function and integrate, right? And in such a way that you get this solution down here. And the reason why you get 0 here is because you're saying that the subspace is orthogonal to the error, right? That's kind of your typical least squares view of finite elements. And then your solution Q lives in some space. Your basis functions live in some space. And this is where now things change depending on what kind of methods you want to use in your approximation. So for example, this superscript subscript CG and DG stand for continuous Galerkin or spectral elements or discontinuous Galerkin. And we, for both spaces, we use nth degree polynomials. And depending on whether you want continuity or not at element edges, you can end up with an H1 space for CG or an L2 for DG. And there's other things you can do as well. And I know FEM has a lot of these options as well. Okay. Let's go back to the integral form of the equation. So we have our residual multiplied by a test function. And now what I did here is I just went back and actually substituted in what R actually is, right? So you have a time derivative and you have a volume integral, 2 volume integrals, okay? And now let's see what happens here. Now we use, we go through integration by parts for this first term here to be able to essentially extract out this flux integral so we can introduce boundary conditions, right? Not just external boundary conditions, but also interior to the elements that you would need in DG, for example. So then if we substitute in for this divergence of the flux term to this term on the far right here, and I sub it back in here, then I end up with this box term here, where you have a phase integral, which is your flux boundary integral, and then you have your volume integrals. Then, of course, at the end of the day, we all solve matrix vector problems. We actually, we go through this rigmarole of integrals, and then we end up with matrix vector problems. So then the matrix form of the equations is you have some mass matrix M, that's what the M is here. You have your time tendency here. You have some other matrix that looks like a mass matrix, but it's actually a phase mass matrix that has inside it, there's embedded a normal vector, N. And then we have a differentiation matrix, which I call the weak form differentiation matrix here, which is given by this term down here. And that's it. That's what you have, right? So again, let's go back to the form that I had just shown you in the previous slide. So here's our time derivative, our numerical, it's our boundary integral that we're going to have to deal with a numerical flux to be able to satisfy the fact that whether you're on a left element or right element, you're going to have different solutions. And this is where you bring in, for example, for DG, all of the nice properties of the method characteristics, for example. You bring in, Riemann solvers. So it's sort of like semi-analytic methods that you bring into solve the PDE, which is really powerful. Okay. So then the first thing we do is we evaluate the volume integrals, which are these two terms on the right here. So I say let R, this right-hand side element-wise vector, be assigned the value of these terms here that I'm showing you here. And then we evaluate the flux integrals, right? So the flux integrals are the ones that are actually, by the way, I should say that in the volume integral, that computation is entirely independent. Every element does whatever they want. There's no information needed across any neighbors, which is great. Then we do the flux integrals, and now you have to worry about who your neighbors are. In CG, so we do this, by the way, for either DG or CG, but in CG, this term cancels at the interior edges of elements because of continuity, right? We still do that operation, but it's our way of being able to handle boundary conditions exactly the same way we're doing CG or DG. Once we do that, then we perform what is known as direct stiffness summation, which is basically constructing the global problem of the finite element strategy. And in DG, all the matrices are block diagonal except for the flux matrix. And that's the one that gives you this global dependence. Finally, at the end of the day, we have to multiply by inverse mass matrix to the right-hand side vector R, and then we evolve the solution in time by your favorite time integrator. NUMA carries two types of CG. It carries one type of DG. XNUMA is only uses CG. And this model that I won't talk about today, but we have another model, a Julia-based code called Atom that runs on GPUs. That's only uses DG. Okay, flux difference DG methods are something that we've been playing with very recently, and I think the elegance of this method is beautiful, and it actually has some powerful advantages, right? So let's start with this. So first, consider that you can actually come up with this discrete integration by parts, which is called the summation by parts property. It's satisfied by Lobato points with an inexact integration. It just means that you basically mimic these mimetic properties of integration by parts, right? So you have the differentiation matrix plus the transpose of the differentiation matrix multiplied by whatever flux term you have is equal to some boundary term. And this is just basically mimics exactly this operation here that you have in calculus, right? Now, the nice thing about this is that this D matrix, this differentiation matrix has this that the row sum is equal to 0. So in other words, if I sum up for all degrees of freedom Mn, Dij becomes 0. Now, why is that important? It means that now I showed you in the first slide that we're using a vective form of say, the velocity field, but I can actually construct in my code conservation forms and advective forms exactly the same way. It's just how I handle the fluxes. It's the only difference. Why is that? Because I can now write all of my equations in this looks like a flux form, right? It looks like a conservative form because D, the differentiation matrix, is hitting both U and Q. So it turns out that when K is equal to J, this yields a conservation form, but when K is equal to I, we have an advective form. That's it. And so our codes are very, very easy, very straightforward to written in exactly the same way, and we just handle the fluxes in a slightly different way. Okay, now let's go back to this conservation law form of our PDEs. And now the only thing is when you bring in more sophisticated fluxes, right? There's a cost that is going to be incurred, and that's going to mean that instead of having your terms looking like this, we actually have a more complicated term that looks like this, where this little open circle is the Hadamard product, right? Which means that now I construct a differentiation matrix and I construct a more complicated flux. And that's where all the power comes in. That more complicated flux gives us a lot of freedom to actually prove rigorously the stability of the method. And you don't really lose anything, right? Because here's a plot. You don't need to see, I know it's kind of a small plot, but all you need to see is that there's a dashed line and a solid line. And these are like, so this one here is order 3 convergence, order 4, and order 5. And the method gives you the expected rate of convergence, even when you use these very complicated fluxes. And just to give you an idea what these fluxes might look like, here is the flux for a kinetic energy preserving scheme that we have in a paper that was just accepted in very recently. And then we also have so here's a kinetic energy preserving flux for the advective form and for the conservation form, where these curly brackets is the usual DG notation for a mean value. And the square brackets is nothing more than just a jump, right? That's all it is. So that's all you need to do. And you can see that whether I have an advective form or conservation form, I just have to change the fluxes. That's all I'm showing you here. Of course, you can actually come up with more complicated entropy stable fluxes, which I don't show you because they have all kinds of logarithms and exponentials, and it's ugly, but the details can be found in our paper reference 5 down here, which is, by the way, where this result comes from. Okay, so let me show you now the power of these methods, right? So here's an example of a baroclinic instability in a channel. It's a complex problem. This is a fully 3D problem. It's essentially the domain size is basically the size of the Earth in the horizontal, right? And so in this case, our grid resolution, or delta X, is 100 kilometers by 100 kilometers in X and Y and 1 kilometer in Z. I know that sounds really coarse, but that's okay. That's what we're looking for. We want to make it coarse. And here's that WRF model that is used by the National Hurricane Center. And so this is a slice at, XZ slice at 500 meters in the the relative vorticity at day 12. And it's a simulation that's usually run from day 0 to about day 15. And unfortunately, very few models don't ever show you more than day 12. And I think there's a reason why. So here is our simulation with NUMA. We use spectral element methods with viscosity, just like WRF does. And you can see that the plots look very similar, right? But what I want to show you is the other two panels. Like if you look at this DG with kinetic energy preserving and DG with entropy stable, I should state that the WRF model, as I told you before, has a lot of dissipation. That's why it's not able to capture this rapid intensification so well. And so the spectral element with the viscosity is more or less our way of mimicking that. We wanted to show that we can get a result that's similar to WRF. But the problem with viscosity, right? This is artificial. You have to tune it. And it's not pretty, right? Now, admittedly, there are ways, and we've worked on this. Well, Sohail's sitting here. We have a paper that, hopefully we'll see the light of day someday, but on actually doing these adaptive viscosity methods, right? So that you don't have to do so much tuning, but it's still an art and not quite a science in my view. And the value of these methods is that there is no viscosity, 0. You just run the code, you do the analysis, you construct the fluxes, and you go. And that is going to be stable no matter what. So the conclusion is that, right, so we're able to get stability with limited dissipation, depending on how you play with the fluxes, with the viscosity rather, which is good for hurricanes, right? Because I said you want to have as little viscosity as possible, but the hyperviscosity still needs to be tuned. On the other hand, the flux differencing schemes that I showed you in this panel here and here use no viscosity at all, but there's no free lunch. There's a catch, right? And the catch is that we're still able to run our simulations a lot faster with this setup, even though we have hyperviscosity and all that stuff, because these fluxes are so expensive, right? But like a friend of mine, David Capriva, once told me, it's when you run with these methods, it's like running with insurance, right? It's not going to break. You can run the code, you can run whatever you want. It's not going to break. So you pay a price, though. Okay, I'm going to switch gears a little bit and talk to you about this multi-scale modeling methods that we've been working on in my group to be able to capture fine scale features in these models without having to pay the actual price of doing an LES simulation. So if you recall, like multi-scale methods, I have a reference here, 6, which is Wynn and E and Bjorn Enquist. If you write your PDE in this general form, so Q is your solution vector and S is all your right-hand side functions, you can represent the solution Q as Q bar, which is the coarse scale solution, and Q tilde, which is the fine scale solution. So here's an example of just a little cartoon of a coarse scale grid, and then behind it, you have them coupled somehow as a fine scale solution, and S is the right-hand side operator. And then if you go through this variational multi-scale approach of Hughes and company, you can actually, after some algebra, you can actually derive these equations and decouple them in the following way, right? So now you have an entire PDE that is what evolves the dynamics of the coarse scale solution, and one for the fine scale solution. But of course, they're coupled as they should be. And this is what we started with when we started doing this work on hurricanes. We said, well, we don't want to run a fine scale solution everywhere because we know that LES solution is going to be extremely, extremely expensive. So let's try this where we basically try to run a fine scale problem that is somehow not communicating that much, right? And I'll show you more about this in a minute, so that it's going to mimic more or less the coarse scale problem. So it's basically run a coarse scale problem and then enrich it with some fine scale features and inject it. That's the idea, right? And we started with this approach, and we ran into some problems with boundary conditions and all kinds of stuff. So we said, we don't know what we're doing just yet. So let's take a step back and let's do what everybody else did first and see if we can learn something from what they did. So then what we did is we started working on these classical multi-scale modeling framework, which is also known as super parameterization in the climate and weather community. And the idea is you consider two PDEs. Oh, I'm sorry, is this blocking you guys here? Yeah, two PDEs. So you have a PDE for the coarse scale problem and a PDE for the fine scale problem. So anything that's capital is coarse scale, anything that's lowercase is the fine scale. And then we have some forcing function F that couples the two somehow. Okay, so here's basically a diagram explaining what I'm trying to say here. So let's say you want to run a 3D coarse scale model, right? And you have here 1, 2, 3, 4, 5 by 1, 2, 3, 4. So 5 by 4 elements, say, that are coarse scale elements. And then each one of these coarse scale elements, you subdivide into a bunch of smaller elements. Right? Now, the idea is that you run these guys not exactly independently, right? So the only time that, for example, well, the fine scale elements all run independently. The only time that they know what's happening to its neighbor is once you couple them through F, capital F and little f, to the coarse scale problem. And then, of course, now this guy then will feel the effect of this guy, and then that's how these guys feel the effect of this guy. Right. So the idea we're trying to do is basically we know where the bottleneck is in PDE solvers, right? It's I'll show you our roofline plot, right? It's in that memory bandwidth bound, 45-degree line, right? And we want to get away from that. We want to push the computation up to the horizontal part of the curve, which is the peak performance of the hardware. Okay, so that's the idea. And the computational savings is that you basically run these fine scale problems at a smaller delta t, little delta t here, right? So let's say you do m of those small delta t's. Once you're done with that problem, you inject a solution back into the coarse scale problem and you move on. So you're really trying to reduce communication. That's as simple as it gets. Okay, and let me show you now a result that we have. So this is a 3D test case. It's a squall line test case. It's actually a thunderstorm simulation. I'm showing you a slice here of the flow. So you'll see, I'm going to play it a couple of times, but the gray here is clouds and the blue is rain, right? And in the background, you have potential temperature. The top panel is just more to show you what the velocity field looks like, but it's really not as important as this panel here. And so you can see the thunderstorm clouds, and I'll play for you one more time. And what you'll see is that the thunderstorm is actually moving towards the right. It starts raining there. And then what we're doing is as the rain hits the ground, we're actually storing that information to know how much rain is being collected by the surface. And that's what this plot down here is going to show. Hopefully, let me see if I can, yeah, right here. So here is sorry, oops, that's not what I wanted to do. So what we did here is here's a fine scale simulation, right, using 200-meter resolution everywhere. And on the far right here is the same code using a 2-kilometer resolution. That's the target that we think we want to be able to use, but we want the solution to look like this one here. So what this middle one does is it did exactly what I showed you. It has a coarse simulation of 2 kilometers, has a fine scale of a little bit more resolution of 100 meters, and we're running the simulation, and we're only injecting information every once in a while. And what you see is this is these plots show the horizontal distance in kilometers of this domain down here, and then the time from 0 to 9,000 seconds. And what we see is this is the amount of rain being collected on the surface. And what it shows you is that these arrows are showing you basically what the speed of the storm is, right? And if you have a fine simulation, the storm is moving in this direction like this. For the coarse simulation, you see that the angle of that storm, the way that storm is moving is a little less, and then the super parameterized or multi-scale modeling framework is closest to this high resolution simulation than it is to the coarse simulation. That's what we're seeing. So this is the first result that we have, and if you're not convinced, the far right panel shows us that collection of water, rain accumulated, and we actually see that sorry, I know there's a lot of information here, but the magenta line is the super parameterized domain, and the black line is the high resolution simulation. So we would like to be as close to the black line as possible and not as quite as the blue line. So you can see that the magenta line, is kind of like in between in some sense, right? It's giving us, the rain accumulation distance is thicker than it is for the high resolution black line, but it's not as wide as the one for the blue. And that's what you see a lot. When you have coarse resolutions, you see that the storms are just very spread out, and the storms move a little quicker. Okay, so this is we got this result literally last week. We still have to do some more analysis, but the good news is that we're starting to see that there is some value in this idea. And in terms of time to solution, we're actually doing very well. Okay, let me see if I can get out of here now. All right, so let's see how I'm doing on time. It's only been 30 minutes, right? Okay, okay. All right, so I told you already that to do hurricane intensification well, we need to have stable methods. We need to have them have less dissipation. We want to cut down the cost further by using this idea of multi-scale modeling, so you don't have to do LES everywhere. And then I mentioned that there's room for time integration. I see Chris Vogel in the back there. I'm sure his ears are keenly interested in this. But anyway, so time integration, right? So let me tell you what we've done in the past in terms of time integration, and there's a lot of room for improvement. Absolutely, I'm a big fan of time integration, and I'm always looking for the bigger, better deal. So we have basically what we've done in the past is we've relied on IMAX methods. So again, you have some, now I'm assuming that all of the spatial operators have been discretized in space. So now I'm only worried about time. So these are basically a set of ODEs that I'm trying to solve. And we construct a linear operator that extracts the stiffness from the equations, right? You can do it by a Newton's method of whatever order you want. And you have to decide whether you want the problem to be linear or nonlinear, and that's another topic. But let's assume that L is linear. Then, and in our case, we want to extract acoustic waves and gravity waves, right? Those are the fastest waves in our system. And then what we do is we make sure that the linear operator has it has these waves. And then I'm going to decompose the right-hand side operator into, this math calligraphy S and F that stands for slow and fast processes in my model. And we've applied standard, ARKs, or in this case, it's going to be S-Turks, right? And we have, for example, a double tableau where the first summation here is the explicit tableau, and then the second one is the implicit tableau. And we have an update step. So these are the stage values and update step. We can also replace the fast operator with a nonlinear operator. But of course, that opens up, this issue of how do you handle these nonlinear problems? Are you using Newton's method? Do you use JF&Ks? Do you construct Jacobians explicitly, et cetera, right? And we actually also work on this as well. For many problems, standard IMAX, the one I showed you here, may not be optimal, right? In particular, if the slow process is expensive to compute and the fast process is inexpensive, there's probably something else you can do. We have tried a lot of different things, and we have a paper that hopefully one of my postdocs, after he left my group, he moved to Brazil, and I can't get a hold of him, but hopefully if he's listening, we need to finish that paper. So, but it's about exactly that. It's about actually constructing fast, nonlinear IMX methods for weather and climate. Okay, so what is another approach? Well, before I start talking about multi-rate methods, what I wanted to say is the way these multi-scale modeling frameworks or these superparameterizations, the way they're typically done, my understanding of it anyway, is that if you are solving, say, the coarse-scale problem with capital Q and a fine-scale problem, little q, right, you solve the entire problem for one big time step, so from time n to n+1, regardless of what stages, how many, what multi-stage method you're using. And once you solve that problem, then you go back and solve the smaller problems of the fine scale problem, where you now couple and that coupling term between the coarse scale and fine scale, that's where there's some magic happening that unclear what others do. But we, in our view, we're freezing that value. Okay, so here I just showed you, I imagine using basically a backwards, BDF1, backward Euler essentially for the coarse scale problem, and then you do something else for the fine scale problem. But regardless, the way we have it now, that simulation I showed you with the squall line, there is an order delta T error in the coupling, right? Because we're doing just the coarse scale solution once, storing that coupling term, and then we're doing the fine scale solution, and we have that coupling term at the end. And of course, that's the poor man's cheapest thing to do, but can we do better? And of course, the better thing to do is to actually couple the stages of both methods, right? So for example, in the case of this, what I have here is slow process, think of it as the coarse scale problem, and as fast process as the fine scale problem. And so you can imagine constructing a multi-rate tableau, which is we've done this, and so the superscript O is for outer loop, and where's the I? There it is. The I here, capital I, is for inner loop. So it's the outer loop is basically the slow process of the coarse scale model, and the inner loop is the fast process or the fine scale model. And so so in this case, let's say you had two stages, right? You run one stage at n+1/2, and then you divide up your fine scale process or your fast process to as many time steps as you would like, and then you apply the same multi-stage method or a different one, right? It doesn't matter. Well, I shouldn't say it doesn't matter. It does matter, but in principle, it looks like it doesn't matter. Why I say it matters is because, so let's think about a standard Butcher tableau where you have, say, some three-stage RK method that looks like this. And if you work out this tableau, then you actually find that this looks like for a three-stage two-rate tableau looks like something like this, right? And what we found when we did this is that if you want to conserve linear invariance, what I see is that you need to have the same tableaus in both the outer and the inner. If you change them, I don't see how to do that. I'm not saying you can't do it. I'm just saying that's not what we found. So that's a problem, right? Because we have to have linear invariance conserved. We want to conserve mass, et cetera. There's other kinds of multi-rate methods, like the multi-step infinitesimal step method of these colleagues down here that give you a very general tableau, but they also have the issue of of not conserving linear invariance. So we started with these MIS idea, and now that's what we've kind of been following, and we not sure where to go from here. But the work, for example, of my colleague at Argonne, Emil Constantinescu, they have these. They use the exact same tableaus, and they can show that they actually conserve linear invariance. But the question is, can you change those tableaus, which we want to change and use different multi-stage methods for both. Honestly, maybe the biggest worry is that this idea of coupling and synchronizing the coarse model with the fine scale model at every stage of the method sounds like a great idea, because you're going to have you'll prove that you'll get the correct rate of convergence in time, but is it too expensive? Because at the end of the day, if it's way too expensive to do this, because now you're communicating more, right? And we're trying to reduce communication. Now I'm saying, I'm going to communicate now. I'm going to increase the communication. So is that something that will we get enough benefit out of it to make it worthwhile? Okay, so this doesn't answer that question, but we have played around with these multi-rate methods, and here we have a baroclinic instability. So this is on the 3-sphere, right? And we use a very cheap ARK1 for hyperdiffusion, which I told you is a very expensive operation. And we use an ARK2 for the remaining operators. And what you find is that, so this is the solution after 10 days. And what you find is that here's a single rate solution here, and now everything is normalized based on that solution. And as you increase the the ratio of how often, how many multi-rate steps you do before you do one outer loop, you actually find that you get about a 30% increase in performance over single rate, which is a really good result because the far right panel here shows a scaling plot that we did with ARK2 back when Miro was still around, my favorite computer of all time. We scaled that, we scaled NUMA up to, 3 million MPI ranks and it scaled perfectly. So if we know that method scales very well. So if we're now getting 30% more performance, that's a good thing. And the reason why that happens is because hyperdiffusion is actually the low-hanging fruit, right? Because it's something that it's not really physical, right? It's there to regularize the equations. So who cares how accurate it is? All you're trying to do is you're trying to just make the model stable. So that's an easy one to do. We have worked on extrapolated multi-rate methods. One of my students defended this PhD thesis a few years ago, and we haven't written a paper yet, but he is, if he's listening, he promised to come to Monterey this summer and finish that paper. And then we have a paper on these implicit time integrators that I mentioned earlier about the guy who ran off to Brazil. Okay, so I'll talk a little bit about still time integration, but now, so I talked a little bit about, okay, let's kind of recap so far. The last thing I did was time integration. I already talked to you about stabilizing numerical methods, these flux difference methods, and then using the MMF to be able to not have to run these LES or fine scale simulations everywhere. But now going back to time integration, to make time integration even more efficient, especially IMEX methods, there's something called a sure complement that you should exploit for a variety of reasons. That's what these next few slides are about. It's so if you think about this, you have basically, imagine shallow water, right? So you have a geopotential height is phi, and then use the velocity field. So let's just talk about the linearized equations. If you discretize them by a strong form, say CG method, then you have a mass matrix, a differentiation matrix that looks like this. And then you see that, oh, okay, if I basically isolate UN plus one and plug it back in here, I end up with this Helmholtz problem that looks like that. And so therefore what that's telling me is that the Laplacian, if you will, of this operator is basically approximated by the, D transpose M inverse D. And the important part here is this M inverse, where we need to be able to construct the inverse of M. And M is the mass matrix. Okay, so, and the nice thing about this is that this problem will be way better conditioned than the original hyperbolic system. Here's an example from a paper we have back in 2010, where the black dots here is the eigenvalues of the no-sure system, and then the red guys are the eigenvalues of the sure system. And these are actually, we get about, sorry, this scale's wrong. This scale is not right. The condition number between these two systems is vastly different. It's like something like on the order of 100 to close to 1 million. And the other important thing is that you also have a smaller system, right? Because this original system here, if you have n degrees of freedom or n grid points, and in this case you have 2n, you have two variables, so you have 2n by 2n system. This system here will just be n by n. And for Euler, right, you have 5 variables. So it looks something like, instead of being order n squared, it'll be order n var times n squared. So it's a much smaller system that's better conditioned. So for general systems of equations, right, if we, after integration by parts, this is the stuff I talked about earlier about element-based Galerkin methods, you end up with something that looks like this. And then now I need to tell you what these fluxes are. So let's say we're using some standard Rusinov flux. So you have the mean value, and then you have a jumping Q. So I can rewrite the flux as the combination of what I call a centered matrix, right? That's only dependent on the element itself, and then a jump matrix that talks to the neighbor, right? And when I plug that stuff back in here, I end up with a matrix vector form that looks like this, right? And what's important is this term right here, this J transpose Q, because now once I integrate in time, I see that this guy here, I can now collect Q of n plus 1 here. And this is like my new, if you will, mass matrix that I have to deal with in my code. And now if J is not empty, now M this term here is going to be non-trivial to invert. It's going to be global. And that's the problem. So why this matters, to construct the Schur complement, we need to isolate terms from one equation to substitute into another, and we need the mass matrix to be invertible, and easily invertible, I should say. One way of getting around this is by separating the linear and nonlinear fluxes in the following way. You can write the total flux as the linear and nonlinear functions, right? And then if we collect this in matrix vector form, we get a form that looks like this here, right? Now, as I said, if this, in this case, if this jump, the linear term is 0, then we can easily isolate Qm plus 1, right? Because this guy goes away here. And I won't go into the details here, but the paper that Sohail and I are working on, hopefully will be done sometime in the next few days, talks about these fluxes. How do we come up with these fluxes? And that's exactly what happens, is you can actually select a bunch of fluxes for the linear and nonlinear terms that allows us to make this jump for the linear term 0, so that we have a mass matrix that's easily invertible. And we can construct a Schur complement. So here's what the North Shore form looks like for the compressible Euler equations using total energy as the thermodynamic variable. Right, here's the pressure here, very, very nice, easy looking pressure. And then by plugging in the rho, u, and e into the pressure term, we actually end up with this. You can see this ugly looking thing here that looks like it could be a Helmholtz operator. It's hard to know. So if you look at the eigenvalues, you actually found that. So eigenvalues, here are the eigenvalues. So the blue here is this is a no Schur form of the system for one type of set of fluxes. The red guys is another no Schur form, right? There's so these guys are purely imaginary. These guys have real and imaginary terms, and then the Schur form that we came up with is very special. I forget what CA stands for, but I like it. It means California, right? I kind of like that. It's California flux. We did it in California. It's the green guy here, and these are entirely all real symmetric, right? So not surprising as expected, real and positive. So symmetric positive definite as expected for a Helmholtz operator. That's one way of knowing that this is some form of elliptic operator, which is great. And if you look at the condition numbers, you see that these are the ones I'm going to show you for the Schur forms versus the no Schur forms. Very, very different. So that's a nice result. We have some results. I'll just show you one for the acoustic wave on a 3-sphere. And so the no Schur is the red line, red and blue lines, and the Schur form is the green line. So fewer iterations as expected, lower time to solution, and the convergence rates all look exactly what you expect. So on that note, 50 minutes in, I have my last 2 slides. Here's my summary. So element-based Galerkin methods, I'm preaching to the choir here, offers elegant way to approximate spatial derivatives for PDEs. They offer much flexibility in terms of geometric and algorithmic. And what I mean by geometric is that, there's something nice about being able to just look at an element and say, here's my construction of that element, right? I don't worry about how I'm going to put that element together, or if it's going to be warped, if it's going to be, a quad, a triangle, a hex, a tet, whatever. And algorithmically, because of the same reason, right? You're always thinking about these element-based approximations that that they have to somehow tie together by either DSS only, like you have in continuous Galerkin methods, or through fluxes and DG. And it just makes it very easy to write code. Like I've used other methods in the past, and once I started playing around with these methods, I'm like, okay, there's no going back. You got to stick to these. I didn't show you too much about these Schur forms, but they offer increase in performance as standalone methods. But also I see them more as also preconditioners, right? Because they are a form of preconditioning, and it's something that we can use to precondition more sophisticated methods, like, for example, these nonlinear IMAX methods that I talked about. Fully implicit methods, I love them. I just can't get them to perform to the same level of performance as, say, my are other methods, right? And it has to do with preconditioning. It just, if you don't precondition things, there's not a whole lot you can do. So I think that there's a lot of value in these methods as preconditioners. Flux differencing, these entropy stable methods I talked about, perform well under the stability metric, right? I told you you can prove rigorously that they're going to remain stable, but they're computationally very expensive. So to give you an example, the entropy stable methods I show you today are about 10 times more expensive than a hyperdiffusion spectral element code. And the kinetic energy is about 5x. And it's not just because of the more complex fluxes. It has to do that we haven't been careful about constructing the IMX methods to be kinetic energy or entropy stable. And so then we're having to use smaller time steps. That's another factor of 2. So really, divide by a factor of 2. So it's 2.5 and 5x really, right? But I do think that there's things we can do. We actually have done this in the paper that we've published, is the number of floating point operations are required by these methods are expensive, but on a GPU they don't seem to be such a big deal. So there's still work to be done. Combining flux difference in DG with Sure is appealing and something we probably should do. Okay, so now back to the last slide, the multi-scale modeling framework, this NUMA that we've developed. It's able to launch one cloud resolving model, which is what I call a coarse simulation, with an arbitrary number of large eddy simulation models in both 2D or 3D. The work completed so far is a squall line test, right? It's only using warm rain. So that means we just have rain. We don't have ice, none of that stuff yet. Future work is to actually run the hurricane simulations with moisture. Right now, we're running the benchmark simulations, meaning that we're running the cloud resolving model with hurricanes and with ice microphysics, right? So once we have those simulations, we can then rerun them with this multi-scale modeling framework. But things are looking pretty good from that standpoint. If you had asked me this about a week ago, I would have said, yeah, I'm not sure how this is going to work, but I think that this is giving us something valuable now. Currently, the cloud resolving model uses MPI only, and the N large eddy simulations or their fine scale models, the way we run it right now is using either N MPI ranks to exploit hardware peak performance, that I'll talk about in a minute. And we're also working on a GPU version. So you're running all of these on separate GPU cards. This is work in progress. So what I mean here is this is the roofline plot I was talking about, right? So here's all our operators. You have different, there's volume kernels, update kernels, gradient kernels, and they're all sitting around this, the memory bandwidth bound part of the curve, right? And of course, we'd like to be up here somewhere where the peak performance is, right? So the idea is that by reducing the amount of communication, you can shove everything up into this area here. You may not get over here all the way, but maybe if you just shove all the stuff a little further up the curve, you'll get better performance. Otherwise, it's going to be, we have all these great exascale computers, but if we only, getting 6% of it, we're leaving a lot on the table, right? That's kind of my worry. Multirate time integration is something that I've been, really a topic of interest for me. It's been primarily a research topic, but I do see that there is some value in using multi-rate time integrators, even if it ends up being too expensive. This idea of coupling the coarse and fine simulations tightly, you at least know that it's going to give you the best solution possible. So that could be your benchmark, maybe, but maybe not the one that you run with all the time. But I do think that it's it's just a powerful way of solving these multi-scale modeling framework problems. And with that, I will stop. Thank you very much.
All right. Thank you. Go ahead.
Yes. So I'm less familiar with NUMA, more familiar with Viscera Dicor. And there, viscosity is treated first order. And so they use this nice, fourth order in space. I think third order time integrated for the dynamics equations, and then they kind of throw on top of it this first order. So when you were talking about your results, where you actually can get the warp results without using hyperviscosity, is that SC plus viscosity using a first order treatment viscosity, or was it actually a higher order?
It's a high order. Yeah.
So I was gonna say, if it was low order, then that's a, you know, other you can quicker capture the thing.
Right.
Like, well,
Right.
you know, we're at least preserving the order of our spatial disposition. Okay.
Right, right. Yeah, so, right, but I was going to say, so the question was about hyperviscosity in the WRF results, right? Yeah, and the thing about WRF is that it's really, I don't know if you ever run WRF, but it's not trivial to figure out like what's in it because it has hyperviscosity, it has Magarinsky, it has a bunch of stuff. So, you know, kind of like, you know, going back to David Capriva's comment about running with insurance, that model's not going to blow up. It's not going to blow up. You're going to run it, it's gonna, you know, but I don't know if I pointed it out, but when I show you that that hurricane intensification problem, increasing the resolution didn't change anything. Like it just runs the same, right? And so it is very stable. But the reason why is because they do so much, you know, they want the model to never break, right? That's the problem with, well, one of the challenges weather prediction is that, you know, probably the more important thing is that the model is stable, right? And it runs fast. Whether it's accurate or not, that's probably lower on the totem pole. No, I'm serious. And that's the challenge that we have as people that work in higher order methods is that you want to run as fast as they do. We know we can get better dynamics, but if you don't match their time to solution, you know, they may not use it, right? That's kind of the reality, right? But I was going to say that if we can run with no viscosity, like I showed in that barracling instability in the channel, and increase the performance of the model to the point where we're close to the models that they have with viscosity, then that's a win. And we haven't done that yet. But I agree, that's the challenge, right? But you know, that to me is the holy grail, right? I think that we know the way forward of how to make something stable without having to rely on viscosity. Because, you know, don't get me wrong, not that viscosity is a bad thing, right? But if I don't have to tune it, that makes my life so much easier. And it just takes time to do that, right? Yeah. Thanks for the question, Chris.
The 2-scale model?
Yes.
Maybe I missed it, but why not just use adaptive mesh refinement? What's the kind of...
Yeah. Oh, that's a great question. So Zanya's question is why not just use adaptive mesh refinement? So we are doing that too, right? So in the coarse-scale models we have, it's basically, we can't pull all our eggs in one basket, right? But the reality is that we're thinking about targeting, like what we want to do in our work here, we wanted to basically be leveraged at some point by some weather prediction system, right? And like dynamic AMR will likely not be used by a lot of centers. I don't know a single center. Like I know the Naval Research Lab is exploring static refinement. So, you know, and I know that E3SM uses static refinement, but it's basically the way we see it is, yeah, maybe I should have explained this better, but in weather and climate, you have the dynamics, which is basically the Navier-Stokes solver. And then you have the physical parameterization that does everything else, radiation, you know, gravity wave drag, you name it. There's a bunch of processes that are at the subgrid scale.
Yes.
That you're not going to resolve unless you're at the 100-meter scale, right? And so that's what we're trying to mimic. We're trying to mimic that subgrid scale processes that you're not going to get. Now, can you do that with AMR? Yes, except you're going to have to, I don't know how to, you would need it everywhere. Right?
I understand.
Yeah, I think that's the but for the hurricane simulations, we are using AMR. Like we're basically using AMR to get into the heart of the hurricane so that we don't have to throw all of our resources throughout the entire global domain. Good question, though.
For the multi-rate time integrators, you mentioned that it's important to preserve linear invariance.
Yes.
Quadratic invariance, like total heritage. Do you care about that? Do you have something about it?
Yeah. So linear versus quadratic invariance. I mean, the way I see it, I would love to conserve everything if I possibly could, right? But I got to draw the line somewhere. And honestly, the what is non-negotiable for me is mass conservation.
Absolutely.
Yeah.
I don't think there is any discussion there.
No, but that's not I'm not saying that's something that is adhered to very closely, right? There's a lot of models that don't in weather and climate, very good models that don't conserve mass. Yeah.
With you on this.
But yes, I would love to. I would love to. I just feel like linear invariance is something I can live with. I can make it happen and within reason.
But do you know of any methods at all, even like theoretically,
To do
to do also energy conservation? So that's something interesting for us to.
right.
We're also looking. Actually, there's a lot
Right.
of connections with many of the things.
Oh, okay. Well, I was going to say this. I mean, the one thing I would say is that if for energy conservation, right, right. So if you're using total energy, I don't know what you use for your variable, right? That's one thing. But in our models, we have that, but that's not the total energy. Using total energy as our thermodynamic variable is only the work that we do for this entropy stable work, right? But for say the actual equations that are being used for weather and climate, this set I showed you in one of my slides, we have potential temperature. That one you can actually show that you can conserve energy up to time truncation, right? But if you have like anyway, so I just ended up having a nice conversation with Maya Talkman about exponential time integrators, right? So that's something that I want to do a little bit more of. But no, I don't know, is the short answer.
Okay, for the phase terms that you have in your fluxes, do they usually just get data? How much of the element data do you need? Do you restrict first and then you do things on the phases, or can you just use one or two layers of the model?
Right. Yeah. So the question is on the phase term on the phase integrals for the flux terms. So we're using Lobato and an exact integration, right? So we use only the terms along the the point right on that edge, and that's it. Yeah. So it's cheap, very cheap.
All right. Last chance, guys. Mine, I know somebody asked here about they logged off, but they asked about formulations and computations with stochastic terms that are different from numerical diffusion. I don't know if that.
Yeah, no, I nothing that we've done along those lines yet. I mean, honestly, the way we see the work done in my group is we're more or less a basic research group that are looking at things like what things can we do to improve the weather models and staying within our wheelhouse, which is basically PDEs, numerical methods, right? That's kind of the bottom line. Yeah.
Thanks. Buddy here?
I'll add, I don't know of any conservative multirate schemes that are out there. Yeah, it's certainly something we're interested in on some dials too.
Okay.
Some thoughts about that, but it's something I'd love to look into.
I know. Yeah.
Very cool.
It could be very interesting. All right. Last one. Can you tell us more about the what do you pronounce it? The Atum?
Atum. Oh, yes. So
I know you said.
yeah. Oh no, this is perfect.
Remember when you said you started working?
Yes. No. Right. So Zanyo asked about the status of Atum. So Atum was a project that was funded by NSF, and we had a collaboration with other universities on building like a new climate system, and we decided Lucas Wilcox at MPS thought that Julia would be a good choice for a language for this model. And then we had a postdoc that now works at Sandia, works for E3SM, who actually developed a lot of that code base. So it's a code written in Julia. It runs on GPUs using something called kernel abstractions, which is Valentin Chiravi at MIT developed. It's actually similar to Akka.
Yeah.
So that's exactly what it is. It's very similar. And so we had experience with Akka before. I didn't talk about it here, but we've used it in NUMA. NUMA has a branch that uses Akka for GPU for running on GPUs. So it was very obvious for us to do something along those lines. That code is still it solves the compressible Euler equations with total energy as a thermodynamic variable. It runs on hexahedral grids. It can do flow in a sphere and just flow in a box. We actually have plans to include things like moisture into that model. Anyway, so that's the code that we've been using for things like running baroclinic instabilities and Held-Suarez test cases. These are these very long simulations that are done in climates, like in standard dynamical course for climate, and those models can run without any dissipation forever. Yeah, and they're stable, and the results look beautiful. I mean, one of my colleagues, who's now at NRLDC, a former postdoc of mine, Jim Kelly, every time he sees a result with these methods, he always says that's the gold standard, because you cannot, to match those results, like we've tried to match them without entropy stable, and trying to lower the diffusion, it's very difficult. The results is just absolutely beautiful.
And I'm just curious, what is your experience with Julia being used for a project like this?
Yeah, no, that is a good question. I have to, I have my moments where I have to think about it carefully about how to say this, right? I think Julia is a great language, and it's something that I would just love, honestly, to move NUMA entirely to Julia. It's going to be a hard sell to do that. Just a lot of leveraging, rewriting of new code and stuff like that. But for this project at TUM and for any other model that I probably would start with Julia. Now, as you know, right, Julia is beautiful if you're, writing, like I use it for my courses. Like when I teach this Galerkin course, I use Julia, and it looks a lot like MATLAB. It's very similar. Of course, once you start running on, performing code like GPU, then it's going to change, right? So it's not as nice anymore to me. That's my impression. But those that are very good at writing GPU kernels, it's all the same. And I like it. It's definitely a language that's growing, and I don't see it stopping anytime soon.
So you'd recommend it for new projects?
I would. Yeah. And I'm not a C++ programmer, so take what I say with a grain of salt. But it really is a very it's a good approach. And yeah. I mean,
right?
Yeah.
Sorry.
No, I was going to say, the last thing I was going to say is that, it was designed by, mathematicians. So, Alan Edelman and his group,
Yes.
It really is meant for people that are math oriented, but it's also a performance scientific computing language. I think it's the third language, right, that's able to achieve, at least petascale performance, right? So it's C, C++, Fortran, and then Julia. And I don't see any. It looks like it's going to continue to develop, and they've done a lot of nice things. It's also really good for example, for data science, right? That's an emphasis that they have for it. And hey, it's free. It's free. Yeah.
I was mostly wondering if you guys could hit some roadblocks, because this is you're doing.
No, nothing yet.
Cool. Very cool. All right. Well, let's thank Frank one more time.
Thank you.